Greetings and welcome to our second section in this unit, section on exponential functions. And so let's just jump right in. You say, well, Kevin, what is so special about an exponential function? What is different than what we've looked at before? Well, I'm glad you've asked, because there's one major difference about exponential functions, and that is that instead of a variable base and a constant exponent, with exponential functions we have a constant base and a variable exponent. Okay, a constant base and a variable exponent. Now, there are some other characteristics of exponential functions we ought to mention. Exponential functions are one-to-one. And because they are one-to-one, that means they're either going to be increasing or decreasing, and that means they will have an inverse. Alright, so knowing a function is one-to-one is a very powerful thing. It tells us quite a bit about the function. If it is the case that our base is greater than 1, then our function is increasing. If it's the case that our base is between 0 and 1, then we have a decreasing exponential function. Two applications that we will see as we move throughout the chapter are the growth function and the exponential decay function. And we will see that there are many, many applications of that as we go in the sciences and business, all throughout mathematics. The exponential function f, given by f of x equal a to the x, is one-to-one. And so when we know that, we know that if my exponents are different, then my base to each of those powers will have to be different. On the other hand, if we know that a to the x1 equals a to the x2, then it must be the case that x1 equals x2. We can see that here in example 1. Notice we've got the same base, so all we need to do is set 2x plus 3 equal to x minus 7, and so x is going to equal negative 10. Alright, we've set the exponents equal to each other. You say, well, Kevin, we don't have the same bases here. Well, that's true, but we can make that happen pretty quickly. We can note that 64 is simply 8 squared. 8 squared to the 3x minus 7. Now we set our exponents equal to each other. X minus 5 equals 2 times 3x minus 7. And so let's see what we get. We get x minus 5 equals 6x minus 14. We can solve for x now. 5x over here. Got a negative 5 equals 5x minus 14. We'll add 14 to both sides. And so 9 equals 5x. And we find out that x equals 9/5. And we'll pull the same little trick here. We'll write these at the same base. So 1/3 is actually 3 to the negative 1 raised to the 2x plus 1. And 27 is 3 cubed raised to the 3 plus 5x. And so our bases are the same. We'll set our exponents equal to each other. And so we've got negative 2x minus 1 equals 9 plus 15x. And so let's see what we get here. 17x equals negative 10, or negative 10 over 17 equals x. Now let's think about what our graphs here look like. And in examples 4 and 5, we will take a look. I want to point out a couple things with exponential functions. Alright, with exponential functions, if I've got f of x equal a to the x, then I know some things. I know that the point negative 1 over a is going to be on the graph, because a to the negative 1 is 1 over a. I know the point 0, 1 is on the graph, because any non-zero base to the 0 power is 1. And I also know that 1, a, is going to be on the graph. So my x value is 1, a to the 1 is simply a. And so if we look here at example 4, we've got f of x equal 2/5 to the x power. We get ready to graph this. Well, let's see, f of -1 equals 2/5 to the -1 or 5/2. F of 0 equals 2/5 to the 0 power or 1. And f of 1 equals 2/5 to the 1 power or 2/5. And so we get ready to sketch this. Here we are at -1, we're up 2.5. At 0, we're at 1. And then when x is 1, we are at 2/5. So we get a graph that looks something like that. Now, we look here at example 5. I'm going to make use of some of the knowledge that we learned in our last unit about reflections and translations and so forth. To do this, I'm going to rewrite this function as the opposite of 3 to the -1 to the x power plus 9. Now we know that 3 to the -1 is 1/3 to the x plus 9. Alright, and so this is now my f of x. This is now my f of x. And we can take these points that we just talked about a little bit ago. For instance, we can take f of -1. Alright, this is going to be -1/3 to the -1 plus 9. Well, this is just going to be the opposite of 3 plus 9, which is going to be 6. So this is going to give me the point -1, 6. Alright, I can take f of 0, here, and so we get the opposite of 1/3 to the 0 power plus 9. We know this becomes -1 plus 9, which is 8, so I get the point 0.8. And if I plug in f of 1, we get the opposite of 1/3 to the 1 plus 9, so we get -1/3 plus 9, which is 8 2/3, or 26/3. So now we get ready to graph that. Alright, and just hang with me here as I plot these. So we've got the point -1, 6. We've got the point 0, 8. And we've got the point 1, 26/3. So that's almost up here at 9. Okay? And when we take a look at this graph, we will see that you notice you've got a horizontal asymptote here at y = 9. Alright, and we'll notice that our exponential function is a decaying function. Alright. And you said, well, I thought you were going to talk about the shifts and stuff like that. Well, if we take a look at the graph of, and let's just look here, let's pull our calculator into action. So you'll give me a minute here, if you will, to activate our calculator. We will see that it's shifted. Let's take a look at, first of all, the graph of y =, let's take a look at the graph of y = 3 to the x. Alright, so here we go. 3 raised to the x power. Alright, so we're going to look at this in the standard viewing window. Alright, now the first thing we're going to do, we're going to hit it with that, we're going to hit that exponent with the -x. So let's take a look now at 3 raised to the -x power. Alright, and let's see what happens there. You'll notice that what we started with, it drew it rather quickly. That's what we started with. Now there's the reflection. Alright, there's the reflection. Keep in mind all this is on the standard viewing window. Now the next thing we're going to do is we are going to put that negative in front. So we've got the opposite of 3 caret negative x. So remember, there's my second graph. Now you should see a flip on that. So let's hit the graph key. And yep, there's the third one. Okay, notice that this guy now has been turned over. And then last but not least, we are going to translate this function up 9 units. So we have negative 3 raised to the negative x. And we're going to add 9 onto that. Add 9. Alright. And so there you go. There you go. So you can think of that one of two ways. You can use our 3 basic points, letting the input be -1, 0, and 1. Or you can look at our basic function and go to the shifts and rotations. Entirely your call. Entirely your call. Now let's graph some more functions here. Looking at example 6, we'll notice that here we're going to assume a horizontal asymptote at the y-axis. I'm sorry, at the x-axis rather, at y equals 0. And so with that being the case, we can just simply consider f of x equal b a to the x. The fact that the horizontal asymptote is the x-axis there is something that I would give you, or something that the information would allow you to figure out. I forgot to type that in there on this particular copy of the notes, but here we go. If we know that y is 1 when a is 0, we can see very quickly that b equals 1. And once we know that we've got f of x equal 1 a to the x, well, x is going to be 1 when y is 5, and so we can see that a equals 5. So what we have here is f of x equal a. I'm sorry, and a we just said is 5. Alright, so I apologize for the delay there. 5 to the x power, and there's my function. Alright, there's my function. Let's give ourselves a little bit of room to work here on example 7. Clear off a little board space, if you will. Oh, notice here we've got y equal 3 staring as a horizontal asymptote. Let's throw a v in. What do you know? Now we're good to go again. So if this is the case, we consider f of x equal b a to the x, so b a to the x, and we're going to add on c here. I know that if I've got a horizontal asymptote at 3, then c must be 3, and then with that in mind, let's take what we're given. We're given the point 0, 4. Okay, so 4 equals b times a to the 0 plus 3. So 4 equals b plus 3. B equals 1. And so now here's where we're at. F of x equals 1 a to the x plus 3. We make use of our point 1, 5. And so 5 equals a to the 1 plus 3. A equals 2. So now we've got a function of f of x equals 1, 2 to the x plus 3. And so if you have questions on those, make sure to bring them in. We'll give you a couple discussion questions to work, a couple homework questions to work there. And now we're going to take a look at Newton's law of cooling. Now, Newton's law of cooling, that's an application that is kind of interesting to me, partly because I'm a big fan of the Law and Order episodes, and I haven't really gotten into the other series like that, but a big fan of Law and Order. And so you're always bringing out the medical examiner to determine how long the body's been dead based on body temperature. Or another way that Newton's law of cooling comes in handy, you can stick a pot roast in the oven, see how long it takes to warm up or cook, and we can use Newton's law of cooling to help us with that. And so I'm a big fan of it, and it's a nice example of exponential functions. So we'll notice here that it says Newton's law of cooling tells us that the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. The face of a household iron cools from 125 degrees to 100 degrees in about a half hour in room that remains at a constant temperature of 75 degrees. From calculus, the temperature of the face after T hours of cooling is given by this particular function right here. Assuming that T equals 0 corresponds to 1 o'clock, approximate to the nearest tenth of a degree the temperature at 2, 3:30, and 4 o'clock. Well, here we go, guys. For part A, notice that T equals 1. 1 hour after 1 o'clock, of course, is 2 o'clock, and so f of T, which here is f of 1, this is equal to 50 times 2 raised to the negative 2 times 1 plus 75. And we can type that into our calculator. We find out that that is 87.5 degrees. If we look at T equal 2.5, 3:30 would be 2.5 hours after 1 o'clock. 50 times 2, so negative 2 times 2.5 plus 75, and this, again, you can type into your calculator, turns out to be 76.6 degrees. And then finally, for the 4 o'clock time here, 3 hours have passed. So f of 3 equals 50, 2 to the negative 2 times 3 plus 75, which this turns out to be 75.8 degrees. And now we'll take a look at the graph of this function. Now let's think about a couple things here. We know that 75 is going to be the horizontal asymptote for this thing. So if I scale my y in terms of 10, 10, 20, 30, 40, 50, 60, 70, 80, and we've got a horizontal asymptote here. At y equals 75. Now, we know that if t is 0, 2 to the 0 is 1. 50 times 1 is 50. 50 plus 75 is 125. So there's 80, 90, 100, 110, 120. There's 125. And so here is the rough sketch of our function that approximates how quickly how quick this household iron is cooling off. So certainly, and they want, I guess, till 4 o'clock. So we're getting at 4 o'clock. We can put that in here somewhere. We're getting very, very close for 75.8 degrees. All right. So if you have questions on that, be sure to bring those in. Finally, one last example here. I've always said that if I can explain things in terms of food and money, then people will get it. And we've got an exponential function here that involves interest. I'm sure it's one that some of you have thought about before. We're going to invest $1,000 at 4%, and our compounding periods are going to be a little bit different. So we're looking at the amount in the account here when we put in $1,000, and 1 plus our interest rate, 0.04, divided by the number of compounding periods, which is 4. This is raised to the 4th power, and I'll let you guys type that in your calculator. That comes out to be about $1,040.60. Now if we do this annually, so we're only doing it one time a year, the amount in the account, A equals $1,000, 1 plus 0.04 over 1 raised to the 1 times 1. Alright, when we type that in, well, that's just $1,040, probably no surprise there. If we do this semi-annually, so twice in a year, the amount in the account, $1,000, 1 plus 0.04 over 2 to the 2 times 1, well, this works out to be $1,040. And if we do this monthly, the amount in the account, 1,000, 1 plus 0.04 over 12 to the 12 times 1, and this turns out to be $1,040.74. And then if we do it daily, the amount in the account, we've got 1,000, 1 plus 0.04 divided by 365. Now folks, remember 0.04, really small number, divided by a fairly big number. We're not expecting that to be very big at all. 365 times 1, and so the amount in our account is $1,040.81. $1,040.81. So we've got some problems to work for class discussion. We've got some problems to work for homework. Certainly bring those with you to class. If you have any questions, we'll be glad to take a look at those.